Tonight, we're going to explore one of the most deceptive ideas in humanity's future beyond Earth: living on the moon. The usual vision is easy to imagine: a bright habitat beneath a black sky, astronauts looking through wide windows at the lunar landscape, a small human settlement slowly becoming a town, and then perhaps a city. But a real lunar home would look nothing like that, because the moon's surface offers no safe place for the human body. There is no air, no protection from radiation, and no atmosphere to burn up the debris constantly striking from space. Daylight lasts for roughly 2 weeks, followed by 2 weeks of darkness, while surface temperatures swing by nearly 300 degrees Celsius. Even the dust is dangerous. It is sharp, electrically charged, and capable of working its way into spacesuits, machinery, habitats, and human lungs. So, the first people who truly live on the moon may spend almost none of their lives standing beneath its sky. Their safest home may be inside an ancient lava tube, buried beneath layers of rock, protected from the very world they traveled so far to reach. That is the hidden reality of lunar settlement. Living on the moon would mean carrying a fragment of Earth with you everywhere. Every breath, every drop of water, every comfortable temperature, and every barrier between your body and death would have to be manufactured and maintained without interruption. By the end of tonight, you're going to understand why the lunar surface defeats almost every familiar idea of a human settlement, how underground lava tubes could provide protection from some of the moon's worst dangers, and why the first lunar residents may feel less like pioneers on a new world and more like terrestrials living in exile. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The moon has been part of human life for longer than recorded history. It appears in our oldest calendars, stories, songs, and myths. It controls the tides, marks the passing of months, and hangs close enough in the night sky to be covered completely by a thumb held at arm's length. It is roughly 239,000 miles away. A radio signal can cross that distance in just over a second, and a spacecraft can reach it in about 3 days. 12 human beings have already walked across its surface. They planted flags, drove vehicles through the dust, collected rocks, and returned safely to Earth. No other world feels so close. That closeness changes the way we think about it. Mars feels like an alien planet, separated from us by millions of kilometers and months of travel. The moon feels almost local. Not another world entirely, but an extension of our own. A place we visited once and could simply return to when we are ready. Because of that, it is tempting to compare living there with surviving in the harshest environments on Earth. Perhaps it would resemble Antarctica, only colder, a desert research station, only more isolated. Somewhere difficult and dangerous, but ultimately manageable with strong shelters, reliable equipment, and enough supplies. That mental picture is wrong at every level. Not difficult in familiar ways, lethal in entirely different ones. Step through an airlock onto the lunar surface in ordinary clothes, and you would lose consciousness in about 15 seconds. You would be dead in under 2 minutes, and for most of that final minute, you would not be aware of what was happening. The vacuum does not feel like holding your breath. It does not give you time to think. It rips the air from your lungs, expands gases in every cavity of your body, and shuts down the brain before the mind can register much at all. There is no discomfort building to a crescendo. There is a sudden subtraction. Antarctica will kill you if you are unprepared, but Antarctica has air. It has atmospheric pressure that holds your blood in the liquid state it needs to be in. It has gravity that feels like home, and a sky that shields you from the radiation streaming in from space. The Atacama is the driest place on Earth, but it breathes. Everest at its summit is brutal, but it has weather, which means it has an atmosphere thick enough to have weather. The moon has none of these things. The surface pressure is so close to zero that the distinction between the moon and the vacuum of deep space is mostly a formality. It is not a harder Earth environment. It is a categorically different kind of hostile. But here's where it gets strange. Even if you solve the vacuum, the radiation alone would make an unprotected stay on the lunar surface a slow death sentence, measured in days, not decades. The moon has no global magnetic field and no meaningful atmosphere. Both of those things, the magnetic field and the atmospheric column, act as shields. On Earth, They absorb and deflect the charged particles streaming from the sun and the galactic cosmic rays arriving from across the universe. Strip them away, and the radiation reaching the surface climbs to several hundred times what a person absorbs living at sea level on Earth. An astronaut working on the surface during a moderate solar event absorbs a dose in hours that would take years to accumulate back home. A permanent resident on the unshielded surface would be looking at radiation exposure that made long-term habitation not merely uncomfortable, but biologically unsustainable. And there is still the dust. Lunar dust is not like beach sand worn smooth by water and wind. The moon has had neither. Its surface has been ground by billions of years of micrometeorite impacts in a vacuum, producing particles with edges that have never been rounded by friction. They are, under a microscope, like tiny shards of broken glass. They cling to everything electrostatically. They worked their way into Apollo suit joints on the first few hours of surface walks and had already begun abrading seals by the time the astronauts returned to the lunar module. A surface habitat would face that dust every time an airlock opened, every time a rover returned, every time any exterior equipment needed maintenance. The dust does not settle. It does not wash away. It accumulates. So the moon is not a harder Antarctica. It is a place where the atmosphere is absent, the radiation is extreme, the dust is a grinding mechanical threat, and the temperature swings from scorching to freezing on a 2-week cycle. The familiar grey face hanging in your sky is the face of a world that will kill you efficiently and without ceremony the moment you treat it as anything less than categorically hostile. Which is why the answer may already be written into the moon itself. Not on its surface, where the hazards stack up and compound, but beneath it, where ancient geology may have done something remarkable. Deep inside the moon, sealed away from the sky, there are tunnels, enormous ones. Tunnels left behind by volcanic flows that moved through the lunar interior billions of years ago, leaving hollow conduits behind when the lava drained. Tunnels that have been sitting in the dark, undisturbed, ever since. The first lasting human home on the moon may be inside one of them. And what daily life inside that home would actually look like is a harder question than most people expect. That figure deserves to be taken apart slowly, under 2 minutes, and each of the things killing you is doing it in a different way. Start with the vacuum. The moon has no atmosphere worth speaking of. What it has instead is called an exosphere, a scattering of gas atoms so thin they never collide with each other. Each atom simply arcs across the sky in a long ballistic curve, alone, never touching anything. The vacuum at the lunar surface is deeper than the vacuum inside a modern particle accelerator by roughly an order of magnitude. It is among the emptiest environments a human body can be placed into. And here is where the intuition breaks down. Most people imagine that vacuum kills by cold, that you would freeze or suffocate slowly. That is not what happens. Vacuum is not a passive absence, it is a pressure difference, and the moment you are exposed to it, that pressure difference acts on you. The air in your lungs pushes outward. There is nowhere for it to go and nothing pushing back. The gas dissolved in your bloodstream, nitrogen that has been sitting quietly in your tissues since the day you were born, suddenly has no reason to stay in solution. It comes out, not slowly. Think of twisting the cap off a bottle of carbonated water. That fizz, that is happening inside your veins, and your saliva boils on your tongue. Not because the moon is hot, because water boils at any temperature above freezing when the pressure around it reaches zero. The liquid on your tongue, at normal body temperature, becomes vapor. Consciousness fades in roughly 15 seconds. Death follows shortly after. This has been the baseline state of the moon's surface for every second of its 4.5 billion years. Every latitude, every longitude, every hour of every long lunar day. The 6 Apollo crews who stood out there were each enclosed in a personal bubble of Earth-level pressure, separated from all of that by a few millimeters of woven fabric and a sealed ring at the neck. That is not a metaphor. That was the actual margin. The temperature is a different kind of problem. The moon rotates once every 29.5 Earth days. A single day-night cycle is nearly a month long, roughly 2 weeks of unbroken sunlight, followed by 2 weeks of complete darkness. And there is no atmosphere to absorb the heat, hold it, redistribute it, or soften any of the transitions. At the equator, the surface reaches about 120 degrees Celsius in daylight, hotter than boiling water. The same rock, the same patch of ground, drops to roughly negative 70 degrees Celsius in the lunar night, a swing of nearly 290 degrees for a surface that has simply rotated away from the sun and back again. In permanently shadowed craters near the poles, where sunlight never reaches at any point in the year, temperatures approach negative 240 degrees Celsius. That is among the coldest naturally occurring temperatures anywhere in the solar system. For machines, this is brutal in a very specific way. Materials expand in heat and contract in cold. Seals crack. Lubricants designed for one regime fail in the other. Electronics built to survive equatorial daylight encounter a different world when the Terminator passes and the temperature drops 200 degrees in a matter of hours. India's Chandrayaan-3 lander made it through a full lunar day, operating exactly as designed. Then, the lunar night came. When the sun rose again, mission controllers waited for the lander to wake up. It never did. A single lunar night was enough. For a human body, which must stay near 37 degrees Celsius, the numbers are simply beyond any biological tolerance. A boot placed in sunlight and a boot resting in shadow can differ by hundreds of degrees at the same moment. There is no equilibrium to find. There is no way to dress for it. But the third hazard is the one that breaks the intuition most completely. Because you cannot feel it. You cannot see it. And by the time it has done serious damage, it has been doing that damage for months. Radiation. Earth protects all life from radiation through two separate systems working at once. The atmosphere, roughly 100 kilometers of air above your head, absorbs incoming high-energy particles before they reach the surface. And the planet's global magnetic field deflects the charged particles streaming outward from the sun, bending them away before they ever reach the atmosphere. These two shields together reduce the radiation dose at sea level to something the human body manages without effort. The moon has neither of these things. No meaningful atmosphere, no global magnetic field. Every galactic cosmic ray, every solar particle, arrives at the lunar surface having lost nothing to any shield. Astronauts aboard the International Space Station, orbiting inside Earth's magnetic field but above most of the atmosphere, receive roughly 100 times the radiation dose of someone standing on the ground. On the lunar surface, the number climbs to several hundred times ground level, depending on solar activity. And then there are solar particle events. A large solar flare can release a sudden burst of high-energy protons that sweeps outward across the inner solar system in hours. When that wave reaches the moon, the surface dose rate can spike to levels that are acutely lethal within hours. Not dangerous over years, lethal within a single day. Here is what most people do not realize about Apollo. Those 6 landings between 1969 and 1972 happened during a period when no major solar particle event struck while a crew was on the surface. The missions were short. The luck held. But it was luck. A large storm during any one of those landings could have delivered doses causing acute radiation sickness to astronauts wearing the very suits keeping them alive. The suits were built for vacuum and temperature. They offered almost no shielding against high-energy protons. For a short visit, the radiation numbers are dangerous, but survivable. For a permanent resident, they become catastrophic. A year on the lunar surface would accumulate doses far beyond the lifetime occupational limit for nuclear industry workers. Cancers, cataracts, damage to the central nervous system and the cardiovascular system. And this is where radiation differs most sharply from the other two hazards. The vacuum stops at the fabric of a suit. The temperature can be managed, at least partially, by a suit's thermal layers and a carefully pressurized habitat. But radiation does not stop at a pressurized wall. It slices through thin metal, through most plastics, through the human body, depositing energy the entire way. You cannot wall it out with the same tools you use to hold in air. 3 hazards, each one independently sufficient to kill or to accumulate damage that shortens a life by years. Each one present constantly, at every point on the surface, with no relief period and no natural shelter. And so far, none of this accounts for the 4th thing the surface does to a human being, which operates on a longer timeline but in some ways is harder to solve. There are 2 more hazards. They do not kill in minutes, they kill slowly, which is almost worse because it means you have to live with them. The moon has no atmosphere. We have established that. But the absence of atmosphere does something else, something that compounds everything already on that list. On Earth, the atmosphere is a shield, in a second sense entirely. Not just against radiation, against physical impact. Every grain of cosmic debris falling toward Earth hits air first. Most of it vaporizes. The streaks of light you see on a clear night are not rocks reaching the ground. They are rocks being destroyed long before they get there. The moon has no such protection. Everything falls through. Most of what falls is tiny. Smaller than a poppy seed. Smaller than the head of a pin. But size stops mattering when the speed is between 10 and 70 kilometers per second. At those velocities, a grain the size of a rice kernel carries the kinetic energy of a bullet. A pebble carries the energy of an artillery shell. And they do not fall occasionally. They fall constantly. Every square meter of the lunar surface is being sandblasted, right now, by a steady rain of high-velocity particles that never stops. The crust itself is the record of it. 4 billion years of continuous micrometeorite bombardment, ground into a fine grey layer by an environment that simply never stops shooting. For an unsuited human, the math is brutal. 1 grain through a helmet is instant depressurization. 1 grain, the size of a rice kernel, the energy of a bullet, death in minutes, as we covered earlier, but now arriving from an entirely different direction. For a habitat, the threat is subtler, but no less serious. Any exposed pressure vessel is being slowly perforated over time. Sensors, radiators, solar arrays, antennas, the outer skin of every module pitted and cratered and gradually chewed away by an environment that does not stop. The engineering answer, in principle, is armor. Walls thick enough and dense enough to absorb that constant rain. But here is where the arithmetic becomes merciless. A wall thick enough to shrug off micrometeorites weighs many tons per square meter, and every kilogram delivered to the lunar surface costs roughly $1 million. You cannot armor a house that way. The economics make it impossible before the engineering even starts. But here is where it gets strange. Because the micrometeorites are not even the worst of it. The worst of it is what they leave behind. Billions of years of hypervelocity impact have not just cratered the surface, they have processed the surface, ground it, pulverized it into a fine grey powder called regolith, which coats every square meter of the moon to a depth of several meters. And regolith looks at first glance like dust, like sand, like harmless inert powder you might brush off a table. It is not harmless, it is not inert. On Earth, wind and water round off mineral grains over millions of years. You can feel the difference between beach sand and fresh broken rock in your hands. The ocean gives sand its smoothness. The desert gives sand its polish. The moon has no ocean, no desert wind, no water at any stage in the process. Every grain of regolith was made by a hyper-velocity impact shattering bedrock, or by a later impact shattering the fragments of an earlier one. The result is not rounded particles, not smooth grains. The result is jagged, angular, glassy shards, some of them 1/100th of a micrometer across, invisible to the naked eye, small enough to float invisibly in the air of a pressurized cabin. Under a microscope, lunar dust looks like broken glass. Under a microscope, it is broken glass. The Apollo astronauts discovered this firsthand, not in the abstract, in the laboratory sense, but in the immediate, maddening, daily operation sense. On missions lasting only a few days, dust was among the most persistent problems of the entire program. It clung to suits by electrostatic charge. The airless surface builds static electricity under sunlight, and dust grains carry that charge and transfer it to anything they contact. Brushing the suits down accomplished almost nothing. The dust came back. It ground into every hinge, every seal, every zipper, every mating surface between components. It coated gloves so thoroughly that after a few hours outside, astronauts could no longer read the small checklists sewn onto their wrists. Back inside the lunar module, the dust that had come in on the suits and boots made the cabin smell like burnt gunpowder. That is not a metaphor. That is what the Apollo astronauts reported. Harrison Schmitt, the geologist on Apollo 17, developed sinus and eye irritation so pronounced that the flight surgeons had a name for it: lunar hay fever. From a few days of exposure, a few days. Now imagine a career. Here's what the dust actually is, chemically. Lunar regolith is roughly 50% silicon dioxide by mass. That is the same compound responsible for silicosis, the lung disease that killed generations of coal miners and quarry workers on Earth. And approximately 1 to 2% of regolith particles are small enough to be inhaled deep into the lungs. not into the upper airways, where cilia and mucus might eventually clear them, into the deep lung tissue, where jagged glass lodges and never leaves. Every model researchers have built predicts that long-term inhalation would produce an accelerated form of the fibrotic lung disease that destroyed the lungs of miners who spent years underground breathing silica dust. Not a distant theoretical risk. An accelerated form. A career on the lunar surface, with current dust control approaches, would deliver that disease more efficiently than the worst mines in human history. And on top of the mechanical damage, there is a chemical threat we do not yet fully understand. Billions of years of unfiltered solar wind has bombarded every surface grain on the moon. That bombardment leaves the surfaces of dust particles bristling with what chemists call dangling bonds, unsatisfied chemical connections that are hungry to react with whatever they touch. Freshly broken glass is reactive. Freshly shattered rock is reactive. Lunar dust is both, simultaneously, and has been energized by solar bombardment on top of that. What those dangling bonds do when they encounter lung tissue, mucous membranes, and the lining of the upper airway is not something we have a complete model for. We know it is not inert. We know it is not safe. The exact mechanism and the full damage profile are still being worked out. Dust control for a permanent settlement is not housekeeping. It is a life support problem, and no one has demonstrated a system that solves it at scale. Stack these hazards together, and something becomes clear that Apollo's brevity was able to hide. 6 missions, 12 people, a total of just over 300 hours of surface time across the entire program. The Apollo record is not evidence that the surface is manageable. It is evidence that very short visits are survivable with extraordinary preparation and extraordinary luck. The surface is not Antarctica with a longer commute. That framing, which you hear sometimes in discussions of lunar settlement, implies that the challenge is incremental, that you dress warmer, bring more supplies, build a stronger shelter. It implies that the systems keeping you alive are mostly intact, and you are supplementing what is missing. None of that is true. Every single system that keeps a human being alive on Earth has been stripped away simultaneously. The air pressure, the temperature buffering, the radiation shielding, the protection from incoming debris, the chemical inertness of the local ground, every one of them, gone at once. There is no partial solution. You cannot dress warmly and manage the vacuum. You cannot build a log cabin from local materials because the local material is crushed glass and silica dust. You cannot rely on any ambient system because there are no ambient systems. Every breath requires machinery. Every degree of body temperature requires machinery. Every unit of radiation dose avoided requires machinery. Every structural surface exposed to the outside is being slowly perforated, coated and degraded by an environment that is simultaneously a vacuum, a radiation field, a thermal engine, and a sandblasting chamber operating at bullet speeds. That is the fundamental problem. Not one hazard to solve. Not a set of independent problems to address one at a time. One total environment in which every protection humans evolved to rely on, every accident of Earth's geology and magnetic history and atmospheric chemistry that makes life possible, has been removed. Whatever survives on the surface, whatever habitation system eventually allows a human being to spend years and not days on the moon, must manufacture every one of those conditions from scratch, using machinery brought from a planet 239,000 miles away, assembled in a vacuum, maintained in the dark, built on a foundation of what is essentially crushed glass. And that is only the catalogue of what the surface does to a human being standing on it. It says nothing yet about the machinery itself. So the obvious move is to build on the surface anyway, and to solve the shielding problem with what is already there. The moon's surface is covered in it. Meters of the stuff, everywhere, for free. Pile enough regolith on top of a pressurized module, and you have, in principle, a bunker. The radiation cannot penetrate deep enough. The micrometeorites cannot reach the hull. The temperature swings are buffered. This is not a fringe idea. NASA and the European Space Agency have both commissioned studies on exactly this approach, and both found the same basic answer. Roughly 2 to 3 meters of loose regolith, stacked on the roof of a habitat, would bring the interior radiation dose to something approaching acceptable for a long-duration crew. 2 to 3 meters. That sounds manageable. It does not sound like a problem. But here is where the arithmetic becomes uncomfortable. 2 to 3 meters of regolith spread across the roof of a habitat with the floor area of a modest apartment is not a thin layer of protective gravel. It is tens of tons. In some configurations, it is hundreds of tons. And every kilogram of that material must be excavated from where it sits, transported to where the habitat is, and placed layer by layer by machinery operating in an environment that is, as we have already established, a vacuum, a radiation field, a thermal engine, and a sandblasting chamber. The dust that has to be moved is the same dust that clogs seals and grinds down mechanical surfaces. Every excavator blade, every conveyor wheel, every joint in every vehicle doing this work is being worn down by the material it is trying to move. You are not simply piling dirt on a roof. You are running a heavy industrial operation in the most hostile workplace ever attempted. And the raw material is the thing that destroys the tools. That alone would be a serious objection. But the thermal story does not cooperate either. One study that examined the temperature behavior of a regolith pile found something that runs directly against intuition. Adding a layer of regolith to the top of a surface habitat actually raised the maximum daytime temperature at the top of that pile. The pile absorbed incoming solar heat. It held it. Before the underlying layers could draw that heat away, the surface of the pile radiated it back outward, concentrating temperature at the top rather than dispersing it. The shielding that was supposed to buffer the habitat was creating its own thermal problem one layer up. Below 30 centimeters, the swings drop sharply. That part is true and useful. Below about 80 centimeters, the daily cycle nearly disappears, and the subsurface stabilizes near the local yearly average temperature. The regolith is, at sufficient depth, genuinely good insulation. The problem is getting it into place at those depths, uniformly, over a large footprint, without destroying the machinery doing the placing. The thermal benefit exists. Reaching it is an enormous engineering exercise, so call it solved. Say the regolith is placed. The radiation dose is down. The temperature inside the module is stable. The micrometeorites cannot reach the outer wall. What remains? The 14-day night remains. 2 weeks of total darkness, during which every solar panel on the surface produces nothing. A crew overwintering through a lunar night needs power from somewhere else entirely. Giant battery banks capable of sustaining life support for 14 days. A small nuclear reactor. Or a rare and narrow option. A ridge near one of the lunar poles that is almost continuously sunlit, because the moon's slight axial tilt keeps a few elevated points in near-permanent light. Those ridges exist. There are very few of them, and they are specific places, not general solutions. Communications remain. A habitat on the near side of the moon has direct line of sight to Earth. A habitat anywhere on the far side requires a relay satellite in lunar orbit before a single word can be sent home. That is solvable. It is also another piece of infrastructure that has to be built, maintained, and replaced when it fails. And the crew still has to leave. Every excursion means suiting up, cycling an airlock, stepping out into the full force of the environment, and returning with dust on every surface of the suit that will then enter the habitat. The shielding protects people who stay inside. People who live on the moon cannot stay inside. They have to go out to work, to repair, to explore, to do the things that justify the cost of being there at all. Every departure undoes, for the duration of that excursion, every protection the buried module provides. You have built a fortress. The battlefield outside has not changed. A buried surface habitat is not a house. It is a fortress on a battlefield that never quiets down, and eventually any serious planner who works through these numbers arrives at the same uncomfortable comparison. The shielding needed to make a surface module livable, the regolith pile, the excavation machinery, the transport systems, the power infrastructure for the long night, the dust mitigation, the airlock cycling protocols, the radiation monitoring and contingency shelter for solar particle events, begins to rival in mass and in cost the habitat it is meant to protect. You are not solving the surface problem cheaply with local materials. You are being asked, in effect, to transport a small mountain from Earth, or to move one on site with machinery that hates its own working environment. The surface is so hostile that adequate protection from it is nearly as expensive as the thing being protected. That is the calculation that quietly changed the conversation. Not in a single dramatic announcement. Over 2 decades of engineering reviews and emission architecture studies, the same arithmetic kept returning. If the surface forces this much shielding, and shielding costs this much to deploy, and even fully deployed shielding still leaves the crew exposed every time they step outside, then perhaps the question itself has been framed wrong from the beginning. The question has been, how do we protect a habitat built on the surface? But there is a different question. What if we do not build on the surface? The moon is old. It has been reshaping itself, very slowly, for billions of years, and there is a possibility that somewhere beneath the surface, the moon has already done most of this work, at a scale no human engineering could match, and at a cost of exactly nothing. That possibility has been waiting underground. The answer, it turns out, was already there, had been there for 1 billion years, and we only learned how to see it in the last 15. The moon has holes in it, not craters. Everyone knows the craters. The craters are dense, bowl-shaped scars from impacts that have been accumulating since the solar system was young. These are something else entirely. They are openings, vertical shafts, some tens of meters across, dropping straight down into darkness with walls that plunge nearly perpendicular to the surface, or even overhang inward. Where a crater gives you a slope and a floor, these give you nothing. Look straight down, and you see shadow that does not resolve. The floor, in the best images, extends sideways beneath the surrounding surface, out of frame, into a void the camera cannot reach. Not a dent. A window into something underneath. The Japanese spacecraft Kaguya, orbiting the moon since 2007, first captured one clearly in 2009. A dark, roughly circular spot about 65 meters across in the Marius Hills region, sitting in the middle of an ancient lava channel. It looked at first like a shadow, the way any depression looks like a shadow from orbit. But here's where it gets strange. When the sun angle shifted, craters behaved as craters do, casting asymmetric shadows that revealed bowl-shaped floors, brightening and darkening predictably as the light moved. This spot did not. It stayed dark on all sides, at every sun angle. The geometry that produced that behavior had only one explanation: a vertical shaft, a skylight dropping straight down into a void below. It was the first confirmed lunar skylight in history, and the first proof that what planetary geologists had been theorizing since the Apollo era was not speculation. The Apollo era was where the idea began. Images from those missions had shown long winding valleys on the lunar surface, structures called sinuous rills, channels carved by ancient lava flows that sometimes simply ended. The flow would trace across kilometers of terrain and then stop, as if the lava had drained underground and never come back out. The idea was that lava tubes might exist beneath those channels. When lava flows on Earth, in Hawaii, in Iceland, in Sicily, it sometimes moves through tubes. The outer skin of a flow cools and hardens, while molten rock continues draining beneath it. And when the eruption ends, the drained skin becomes a hollow tunnel. That tube can persist for thousands of years. The physics that produces tubes on Earth should have operated on the moon as well. And in 1/6 of Earth's gravity, the tubes could be enormous. Models suggested widths of tens to hundreds of meters, lengths of kilometers. Ceilings that on Earth would collapse under their own weight could hold indefinitely on the moon. If a tube's ceiling collapsed in a single spot, what you would see from orbit would look exactly like what Kaguya found. NASA's Lunar Reconnaissance Orbiter arrived in 2009, carrying a narrow-angle camera capable of resolving features less than a meter across. Over the next 15 years, its systematic imaging of the near and far sides produced a catalogue of more than 200 confirmed pits. They ranged from about 5 meters across to more than 100. Some were shallow depressions with sloping walls, others were deep, sharp shafts with vertical or overhanging walls, a geometry that can only form when something below has collapsed, leaving the ceiling unsupported until the opening forms. 200 pits, all of them windows, none of them craters. 3 drew the most sustained scientific attention. The first was the original, the Marius Hills pit, in a region dense with the remnants of small ancient volcanoes. It drops about 40 meters to a rubble-strewn floor whose edges extend sideways into shadow the camera cannot resolve. In 2017, a team from Purdue University and JAXA reanalyzed data from Kaguya's radar sounder, an instrument that had sent radio pulses into the lunar subsurface during the mission's operational life. The reflections that came back were consistent with a large subsurface void extending several kilometers, running roughly parallel to a nearby sinuous rill, not a confirmed tube. But the pit, the geology, the gravity data, and the radar together made a picture that was difficult to explain any other way. The second was the Mare Tranquillitatis pit, on the far side of the moon, in the region called the Sea of Cleverness. About 100 meters across, in terrain that is older and less well understood than the near-side Maria, featuring bright, swirling patterns on the surface tied to localized magnetic fields whose origin is still debated. The third was the one that mattered most. The Mare Tranquillitatis pit sits in the Sea of Tranquility, roughly 400 kilometers from the Apollo 11 landing site. Armstrong and Aldrin walked the surface of that sea for less than a day, and never knew a hole of this size existed within a short distance of where they stood. It is about 100 meters across. It drops approximately 130 meters to a rubble floor. That makes it the deepest confirmed pit on the moon. In July 2024, a team led by Leonardo Carrere and Lorenzo Bruzzone at the University of Trento, working with colleagues at the University of Padua, published their findings in Nature Astronomy. Their achievement was not a new observation. The Lunar Reconnaissance Orbiter's mini-RF radar sounder had passed over the Tranquillitatis pit in 2010 and recorded its echoes. But the tools available in 2010 were not sufficient to unpack what those echoes contained. The Italian team spent years building a new signal processing pipeline, a method for reading patterns in old radar data that no one had previously been able to resolve. When they applied it to the archived 2010 records, a pattern emerged that the raw data had been holding all along. Some of the radar reflections were not coming from the pit floor. They were coming from a cavity extending sideways beneath the surface, tens of meters beyond the visible opening, at least approximately 40 meters wide. A space connected to the surface by the shaft, running underground, real and physically present. Not inferred from surface shape, not modeled from analogy to Hawaiian tubes. Detected. For the first time in the history of planetary science, the existence of a genuine cave conduit on another world had been directly demonstrated by remote sensing. A void beneath the Sea of Tranquility, connected to the surface by a shaft, physically demonstrated to be there. Think about what that means for the 200 other pits, the 200 other windows into darkness waiting across the lunar surface. If the Tranquillitatis pit leads into an intact lava tube, and if similar tubes lie beneath even a fraction of those other openings, then the moon may already contain what no surface engineering has been able to build. Natural vaults of solid volcanic basalt, some tens of meters overhead, sealed for 1 billion years, waiting in the dark. Protection from radiation, from micrometeorites, from the thermal cycling that destroys machines and suits. Not manufactured, not transported from Earth at cost per kilogram. Already there. It may be a way of living on the moon by not living on the moon at all. But a hole in the ground is not a house. And what happens when you try to turn one into a home is where the story becomes genuinely strange. Before going any further, it is worth slowing down. Not to deflate what the Tranquillitatis detection means. To be very careful about what it actually shows and what it does not, because this is exactly the point where the story usually gets ahead of the evidence. Here is what we actually know in decreasing order of confidence. First, the confirmed observation. The pits themselves have been directly imaged. More than 200 of them exist as photographs. Their sizes, depths, and floor shapes have been measured to within a few meters. That is not inference. That is not a model. Cameras looked at the moon, light came back, and the images are there to examine. Second, also confirmed, though the technique is new. At least one pit, the Mare Tranquillitatis pit, has been shown by radar to lead into a subsurface void, extending sideways from the base of the shaft. The Italian team's signal processing pipeline produced a genuine detection. The precise dimensions carry uncertainty, as any new technique does, but the cavity is there. The radar reflections require it. Third, a reasonable inference. Many of the other pits share the geological characteristics of the Tranquillitatis pit. They sit in similar volcanic terrain. They show similar geometry. From that similarity, it is reasonable to think other pits probably also connect to subsurface voids. Probable is not the same as confirmed. It is a reasonable inference, not a second detection. Fourth, a plausible model. From theoretical work on lunar volcanism and from data collected by NASA's Grail mission, large lava tube networks may extend for kilometers beneath the Maria, connecting some pits into an interlinked system of passages. Plausible, backed by supporting data. but no one has ever directly mapped an intact lava tube extending more than a few tens of meters. That fourth step is where the popular account and the scientific one begin to separate. And the gap is worth understanding, because it has direct consequences for anyone thinking about building a settlement inside one of these structures. The GRAIL mission is why the confidence in large voids exists at all. GRAIL, which stands for Gravity Recovery and Interior Laboratory, consisted of two identical small spacecraft, nicknamed Ebb and Flow. They orbited the Moon in tandem from 2011 to 2012, trailing each other at a precisely measured distance. As they flew over the Moon's uneven surface, the irregular pull of gravity tugged one spacecraft slightly before the other, compressing or stretching the distance between them by tiny amounts. By tracking those tiny changes, scientists could map the density of the rock below. GRAIL produced the highest resolution gravity map of any body in the solar system, including Earth, detecting density differences at scales of a few tens of kilometers. In several regions of the Mare, that map found density anomalies, patches where the underlying rock appeared less dense than the surrounding basalt. Some were consistent with buried impact features. Others sat in geometries matching the shapes that ancient lava tubes would be expected to leave behind. In 2015, a team at Purdue University led by Rohan Sood and Loic Chapaz analyzed those anomalies and suggested that certain ones could represent intact lava tubes with cross-sectional widths of up to several kilometers wide. The largest known lava tubes on Earth are hundreds of meters across, and they count as remarkable geological features. On the Moon, lower gravity means the mechanics could support far larger structures. In principle, the Moon could contain tunnels wider than some Earth river valleys. But here is where it gets strange. GRAIL cannot see a single tube. What GRAIL detects is a gravity signature, a region of slightly lower average density, and it cannot distinguish a single enormous hollow from many smaller voids grouped together, nor prove that any anomaly is a hollow rather than simply lower density rock. Perhaps fractured basalt or ancient porous lava flows, with no open space at all. The gravity signature is consistent with tube networks. It does not require them. Anyone reading a headline that says the Moon contains kilometer-wide underground caverns should mentally translate that sentence into something more accurate. Gravity measurements are consistent with the possibility of such caverns. That is a meaningful scientific result. It is not the same thing as a discovery. And if those caverns do exist, no one has observed them directly. As of 2026, the kilometer-long cave networks visible in artist impressions of lunar cities are a hypothesis, consistent with what we see. Not surveyed, not mapped, not entered. Why does that distinction matter? Not in an abstract academic way, in a very concrete engineering way. When engineers plan a settlement inside a pit, they are not planning inside a structure whose walls, ceiling, floor, temperature, chemistry, and structural stability have been characterized. They are planning inside a shape they can only guess at from the outside. That is a different problem entirely. Even for the best characterized feature on the Moon, the Mare Tranquillitatis conduit, the limits of current knowledge are severe. We do not know the height of its ceiling. We do not know the length of its floor. We do not know how far its walls extend before the passage continues into a larger chamber, narrows into a choke point, or ends in collapsed debris. The Trento team was careful to say so. Everyone in the field is careful to say so. It is only when the findings filter through second-hand reporting that the caves become enormous cathedrals mapped in perfect three-dimensional detail, ready for construction crews to move in. They are not that. They are, for now, one confirmed conduit with unknown dimensions, and more than 200 other openings whose interiors remain entirely uncharacterized. That is still extraordinary. The science is genuine, the implications are significant, but an engineer designing a habitat cannot work from a hypothesis. They cannot anchor a pressurized floor to a ceiling height they have never measured. They cannot plan atmospheric containment around a wall geometry they cannot see. The gap between consistent with and confirmed is exactly the gap between a promising possibility and a construction site. The GRAIL anomalies may be real hollow tubes. They may be fractured rock. The Tranquillitatis conduit may open after a few dozen meters into a chamber large enough to house a city block, or it may taper into rubble. We do not know. We do not yet have the instrumentation on the surface or in the right orbit to find out. And that unknown is not a footnote to the lava tube story. It is the next chapter of it. Grant all of that. Grant every caveat from the last chapter. Grant that the conduit may taper into rubble after a few dozen meters. Grant that the ceiling height is unknown, the floor geometry unmeasured, the wall extent unresolved. Grant the most conservative version of the claim anyone could reasonably defend. Even then, what that rock does for you is almost hard to believe. Here is the arithmetic, taken one hazard at a time. The first is radiation. Cosmic rays and solar particle events are stopped by mass. On Earth, the atmosphere provides the equivalent of roughly 10 meters of water overhead, absorbing and scattering the worst of what comes in from outside. On the lunar surface, with no atmosphere at all, that shielding must be manufactured. Engineers reviewing regolith shielding have converged on a minimum of 2 to 3 meters of packed soil over a habitat footprint. That is tens of tons for a modest structure, moved and placed by machinery operating in the most hostile workplace ever attempted, using a material that destroys the machinery moving it. The radiation problem on the surface is not abstract. It is a construction problem of enormous practical weight. Under a lava tube, that problem does not need to be solved. It has already been solved. The Mare Tranquillitatis conduit sits beneath more than 100 meters of solid basalt, not 100 meters of loose regolith, which is fluffy upper soil with a density of roughly 1.5 grams per cubic centimeter, but solid volcanic rock at roughly 3 grams per cubic centimeter, denser by a factor of 2. The mass overhead is not a thin, protective layer. It is a geological feature, and what that feature does to the radiation environment inside is staggering. 100 meters of basalt reduces the cosmic ray dose to something close to what a person receives living on Earth at sea level. A solar particle event that would kill a crew standing in the open on the surface. An event delivering a lethal dose within hours would be effectively invisible inside. A person could, in principle, work an entire career beneath that rock and never accumulate a troubling dose. You cannot buy that with hardware. The mass required to replicate it from scratch, launched from Earth at current cost per kilogram, would exceed the budget of any realistic program. The Moon has already put it there. That is the first of 4. The second is temperature. The lunar surface swings nearly 300 degrees between noon and midnight, on a cycle almost a month long. Section 4 established what that does to machines, to seals, to lubricants, to every system that depends on materials behaving within a predictable range. The problem for a surface habitat is not just the extremes, but the relentlessness of the cycling. The thermal fatigue accumulating across every component, across every day of operational life. In 2022, Tyler Horvath at UCLA led a study using thermal measurements from the Diviner instrument on the Lunar Reconnaissance Orbiter. Diviner had been mapping the moon's surface temperatures for years. Horvath's team examined the permanently shadowed floors of certain pits, including the Tranquillitatis pit, looking at what the instrument recorded, where sunlight never reached. What they found changed the thermal picture entirely. The shaded interiors were not cold. They were not swinging through extreme cycles. They were sitting at an almost unchanging temperature of roughly 17 degrees Celsius. Not 17 degrees as a daily average. 17 degrees as a stable, persistent value that held while the surface directly above swung 300 degrees in either direction. Roughly what a slightly cool office thermostat might be set to. Room temperature, sustained by nothing more than the insulating properties of tens of meters of rock and regolith. The explanation is straightforward once you see it. Rock conducts heat poorly, and loose regolith conducts it worse. The daily temperature wave penetrates downward, but even at 80 centimeters depth, the swing is nearly gone. At tens of meters, in a permanently shadowed cavity, the temperature settles at the long-term average and stays there. The surface roasts and freezes. The interior does neither. A settlement inside that cavity would need modest thermal control, not the enormous heating systems required to keep equipment alive through 2 weeks of total darkness. Not the punishing radiator arrays needed to shed the noon heat. The moon has done the hard part. That is the second of 4. The third is micrometeorites. Rock is opaque to fast-moving particles, the way water is opaque to a diving pebble. The moment you are under overhead cover, the constant sandblasting stops. Not reduced, stopped. The chance of a micrometeorite punching through tens of meters of basalt to reach an interior chamber is, for any practical calculation, 0. A surface habitat accumulates perforations across every day of its operational life, in sensors, in radiator surfaces, in hull material. A cave habitat does not. The overhead rock absorbs every incoming grain before it gets close. This one requires no elaborate accounting. The protection is absolute. That is the third of four. The fourth is dust deposition, and it is more nuanced than the others. The rock overhead does not stop electrostatically charged regolith from being tracked inside on suits. That problem follows a crew anywhere on the moon, into any structure they enter. But the constant arrival of new dust from above, the slow accumulation of fresh material onto every panel, every radiator, every seal, every joint exposed to the open surface, that process halts inside a sealed cavity. Micrometeorite impacts on the surface launch tiny grains on ballistic arcs. Those grains come down somewhere. On the surface, they come down on everything. Inside a sealed tube, they do not. Once a section is cleaned, it can, in principle, stay clean. For a settlement depending on solar power systems and mechanical equipment with tight tolerances, that matters. Not at the scale of radiation, but not trivially either. That is the fourth. Add them together and something extraordinary emerges. The surface is dangerous because it exposes everything simultaneously: radiation, thermal cycling, micrometeorite bombardment, and continuous dust accumulation, all operating at once, all compounding. The interior of a lava tube removes 4 of those exposures together, using nothing but ancient rock. No hardware, no maintenance budget, no energy cost, no moving parts. 1 billion years of volcanic geology sitting there, doing the work for free. It is without exaggeration the single most powerful piece of natural infrastructure anywhere in the inner solar system for a species trying to leave Earth for good, and it has been waiting there for well over 1 billion years. Which raises the obvious question: if this is so good, why aren't we there already? The answer is where the story sharpens back into difficulty. Because natural protection is not the same as a natural home. The rock solves 4 of the 5 worst hazards, but the 5th is not a hazard the rock can touch. And the 5th is where nearly all of the hard work lives. The 5th is not a hazard at all. It is a category. It is everything that still needs to be built. Start with the most basic question. How do you get in? The Tranquillitatis pit is a shaft, not a ramp, not a slope you could walk or drive down at a careful angle. The walls, in every orbital image taken so far, look like the sides of a well, vertical in most places. In some places they overhang, leaning back over the void below. Anything descending would need to swing outward from the rim into open space just to avoid being dragged against the wall on the way down. And what waits at the bottom of that descent is not a flat and cleared floor. It is a chaotic pile of boulders and shattered basalt, the accumulated debris of everything that has slumped, fractured or fallen since the ceiling first gave way. The drop from rim to debris field is roughly 100 meters. That is a 30-story building, straight down onto rubble. Getting a robot into that space is not impossible. Tethered rover designs have been proposed. Small crane concepts have been sketched out by mission architects at more than one space agency. The engineering challenge is real, but it is within the reach of existing technology. But here's the thing. None of those concepts has ever flown. As of 2026, no human-made object has ever entered a confirmed lunar pit. Every image of the interior of every pit in the catalogue of more than 200 confirmed skylights has been taken by cameras looking straight down from orbit. The floor of the Tranquillitatis pit has been photographed from above. It has never been touched, sampled, or visited by anything we have built. The cave has been seen. It has not been entered. And even setting access aside, there is a deeper problem. We do not know what is inside. The Trento radar result told us that a cavity extends sideways beneath the surface. It told us roughly how wide the void is at the level the radar probed. What it did not tell us is the height of the ceiling above the floor. It did not tell us the shape of the walls. It did not tell us whether the ceiling is a smooth, stable arch carrying enormous compressive load, or a fractured zone riddled with hairline cracks ready to drop basalt without warning. Earth's lava tubes offer both possibilities. Some have ceilings that have stood for tens of thousands of years and would support the weight of a small city. Others have thin crack sections partially filled with rubble, places where the tube has already begun collapsing from within. Which of these describes a given stretch of the Tranquillitatis conduit cannot be determined from orbit. It can only be measured on site, by instruments that have not yet been built, delivered by missions that have not yet flown. The length of the conduit is unknown for the same reason. Is the passage a short pocket, a few tens of meters ending in a rockfall? Or is it a segment of a much longer tube, one that runs for kilometers beneath the Sea of Tranquility, opening into chambers, branching, continuing past the reach of any radar we have currently turned toward it? The Grail gravity anomalies hint at large voids in the Maria, but cannot follow a specific conduit. The mini RF radar that revealed the Tranquillitatis cavity cannot see far enough along the passage to resolve the question. A rover equipped with its own ground-penetrating radar, moving through the interior, could answer it. That rover does not exist yet. Then there is the question of what coats every surface inside. The interior of a lava tube sealed since the moon's last volcanic era is almost certainly cold, dry, and chemically inert. There is no weather down there, no water, no reactive gases. In that narrow sense, the cave is protected. But the walls and the floor are not pristine. During the collapse that opened the pit, Regolith fell in. And for the 3 billion years since, thermal cycling and micrometeorite-induced seismic shaking of the ceiling have been shedding fine dust from the rock above, letting it settle onto every surface below. Some of that dust was exposed to solar wind during and after the ceiling collapse. It carries the same reactive, jagged glass character that damaged suits and invaded equipment during the Apollo missions. The cave is protected, but it is not clean. Here is where it gets strange. The most non-obvious problem with a lava tube as a habitat is not the descent, and it is not the unknown interior. It is a geometry problem with the opening itself. The overhead protection that makes a lava tube extraordinary stops abruptly at the collapse hole. Directly beneath the pit opening, during the 2-week lunar day, sunlight falls onto the debris field below. Radiation streams in through the gap. Micrometeorites can enter through the opening just as they enter any unshielded space on the surface. Anything set up directly under that hole is not sheltered. It is exposed. The protection exists only where rock sits overhead. And rock sits overhead only in the conduit proper, away from the pit, away from the debris field, beyond the opening. Which means the useful space is not the space you see when you look down the shaft. The useful space is around a corner. The system is shaped like an L. The vertical drop is one arm of the L. The shielded conduit is the other. To reach the arm that offers protection, you must descend the pit, cross the debris field at the base, and move off the rubble and into the passage, past the edge where the rock closes back overhead. Getting people, power, air, supplies, and equipment from the surface, down the pit, across the chaotic debris, and into the sheltered section is an engineering sequence of its own. It is not one problem. It is a chain of connected problems, each of which must be solved before the next one becomes accessible. None of this erases what the Trento result found. The cavity is real. The shielding is extraordinary. The natural infrastructure is the hardest part, the part no rocket could reasonably deliver, and the moon has already provided it, at no cost. But the pit and conduit system is best understood not as a ready-made home, but as a partially finished building. The walls are there. The ceiling is there. The shielding is there. The entrance, the fittings, the utilities, the life support, the lighting, the communications infrastructure, and every square meter of livable floor still have to be constructed and installed by humans and machines working at the bottom of a shaft on another world. The moon has given the future settlers the hardest part for free. It has given them the shell. It has not given them the house. And that shell has been sitting in the dark for a very long time. The conduit beneath the Sea of Tranquility was already 1 billion years old when the first fish crawled out of the shallows of an Earth ocean. The rock overhead has protected its interior through the entire history of complex life on this planet. Every animal that ever lived, every forest that ever grew, every civilization that ever rose, all of it unfolded while that passage sat cold and silent and unchanged, waiting. In the last 15 years, a handful of orbital cameras and one careful piece of radar signal processing have revealed it to a species that might, in the coming century, become the first thing ever to enter it. That is the ledger so far. The gifts are real, the burdens are real, and the burdens have barely begun to be counted. Those burdens begin with a decision that cannot be deferred. Standing at the rim of the Tranquillitatis pit, Every abstraction about lunar settlement collapses into a single hard question. The shielding is there. The rock is there. But everything else, every wall, every wire, every liter of breathable air, has to come from a planet 250,000 miles away or be made on site from crushed volcanic glass. And before any of that work can begin, a planner has to choose one of exactly 3 approaches. Each one solves part of the problem. Each one creates a new set of problems in return. And the cave only looks like the obvious answer until you see what it costs. The first approach is the one that shows up in most concept art. Bring pressurized modules from Earth, land them on the surface, connect them, and pile regolith on top until you have enough mass overhead to matter. It has a genuine virtue. The modules can be built in a factory, tested in a vacuum chamber, qualified on Earth before they ever leave the ground. That is not a small thing. Every kilogram that arrives on the moon has been to space before and survived it. But here is where the arithmetic becomes uncomfortable. NASA and ESA studies both arrive at roughly the same number for what counts as acceptable shielding for a career-length stay. 2 to 3 meters of loose regolith overhead. That sounds manageable until you work out what it means in tonnage. Over even a small habitat's footprint, 2 to 3 meters of regolith is on the order of 100 tons of material. That material does not arrive piled in place. It has to be excavated from somewhere nearby, moved, and stacked by machinery working in vacuum across a temperature cycle that swings nearly 300 degrees over a single fortnight, in a dust environment that is, as we have already established, actively trying to destroy every moving part it touches. The shielding is free, moving it is not. The second approach sounds like it solves that. Dig a pit, lower the habitat into it, backfill from above, thicker shielding, more evenly distributed, no pile to worry about sliding or settling. It is a reasonable sounding plan. Wait, lunar regolith is not soil, not loose dirt, not sand. It is a densely packed, cohesive mixture of glass shards compacted by billions of years of micrometeorite impacts, in places approaching the density of soft rock. Any excavator working in it has to grind, cut, or blast. All 3 methods produce clouds of the same jagged airborne particles that destroyed Apollo hardware in a matter of days. All 3 must be managed in vacuum, and all 3 chew through metal tools at a rate that is, by every engineering estimate, remarkable in the worst possible sense. One study put it plainly. A single lunar excavation project large enough to bury even a small habitat would probably consume more machinery, more spare parts, and more crew hours than the entire Apollo program combined. Not Apollo's surface time, the entire program, every rocket, every mission, every hour of training, every component manufactured for every Saturn V, all of it, to dig one hole. That was the second option. The third is the one that keeps rising to the top of every serious planning document. Stop trying to manufacture protection you cannot afford to move. Use protection that already exists. Find a natural cavity, lower habitat modules through the existing skylight, set them up under the overhead rock, and let the ceiling that has been there for billions of years do the shielding that would otherwise require moving a small mountain. The mass advantage is not marginal. A Colorado School of Mines study calculated that using a lava tube instead of piled regolith could cut the total shielding-related construction mass at the site by more than an order of magnitude. That is the difference between a project requiring dozens of heavy lift launches and one requiring a handful. In an environment where every kilogram costs what it costs to reach the lunar surface, an order of magnitude is not an engineering preference. It is a civilizational difference. So the cave wins. The numbers say so. The physics says so. Every comparison says so. But here is where it gets strange. A surface habitat can be reached by driving a rover across open ground to its airlock. A buried habitat can be reached by descending a purpose-built stair or elevator to a sealed door. A lava tube habitat must be reached by descending 100 meters of vertical shaft, crossing a chaotic debris field of shattered basalt, and traveling around the corner of an L-shaped conduit to reach the section with solid rock overhead. That is the route for every gram of cargo, every crew member, every replacement part, every piece of equipment that breaks and needs to be swapped, every rescue team if one is needed, every evacuation route if the situation demands it. They all go through the same opening, the same single shaft. There is no other way in. Civil engineers have a term for a facility with exactly one point of entry and exit. They call it a single point of access facility. On Earth, building codes exist specifically to prevent them. The rules that govern how hospitals and schools and data centers are designed require multiple independent egress routes, precisely because a facility with one entrance is a facility where a single failure blocks everything. A blocked stairwell, a stuck door, a collapsed passage. Any one event and the facility is sealed. The people inside have nowhere to go. A lava tube settlement, as currently conceived, is exactly what those codes are designed to prevent. Not a minor inconvenience. A structural vulnerability at the heart of the design, which means the cave's enormous advantage, the rock overhead, the free radiation shielding, the thermal stability, the order of magnitude reduction in launch mass, all of it rests on a foundation with a single, narrow, 100-meter deep throat. And that means the very first infrastructure any serious cave settlement requires, before a single habitat module is lowered into the conduit, before a single bolt is turned in the dark, is a safe way to move things down that shaft. That problem has to be solved first. Everything else waits behind it. Building a safe way down the shaft turns out to be only the second step, not the first. And walking through the actual order of operations shows just how much has to happen before anyone moves in. The mainstream engineering thinking, drawn from concept studies at NASA's Jet Propulsion Laboratory, the European Space Agency, and academic groups at the University of Arizona and the Colorado School of Mines, imagines the sequence unfolding across several successive robotic missions. No human crew is committed until late in that sequence. Very late. The instinct is to picture astronauts arriving and beginning construction, the way a building crew shows up to a cleared lot. That instinct is wrong. The lot has to be measured first. And no one has been inside to measure it. That is where Phase 1 begins. Before a single module can be designed to fit the interior, a robot has to go down and map it. The geometry of a specific pit's interior, its width, its ceiling height, the shape of the debris floor, the exact dimensions of any conduit extending sideways from the base, none of that is known from orbital imaging alone. LRO photographs the Tranquillitatis pit from directly overhead. It does not tell engineers how far back the cave runs, how high the ceiling sits above the rubble, or which sections of the floor are flat enough to support a structure. You cannot design a habitat for a room you have never measured. The technique for getting that measurement has been demonstrated in prototype on Earth. ESA developed a concept called Daedalus, a spherical rover roughly the size of a beach ball, carrying LIDAR, cameras, and radar, designed to be lowered on a cable from the pit rim and rolled across the debris field below. NASA JPL proposed a similar concept called Moon Diver. Both represent the kind of machine that has to enter a specific pit before any architecture for that pit can be drawn. Neither has flown, neither is currently funded to fly. That is where Phase 1 stands right now. The mission that must happen first has not been approved, and without it, every subsequent phase is planning for a room whose dimensions remain unknown. But here's where it gets strange. Even after a reconnaissance mission returns its data and engineers know the interior geometry, Phase 2 cannot be humans descending to begin work. Phase 2 is building the access system itself, the permanent transport infrastructure between the surface and the cave floor, and it has to be completed entirely by robots before any crew arrives. The simplest version is a heavy-duty cable elevator, a vacuum-adapted, low-gravity version of the systems used on Earth, to lower workers into deep mines. A more ambitious design cuts or builds a permanent ramp into a pit wall for wheeled vehicles. The most expensive and most redundant option installs multiple independent access systems from the start, so that a single failure does not seal the settlement below. Whichever design is chosen, the logic is the same. The crew cannot install their own escape route while relying on it to reach the work site. The access infrastructure has to exist before anyone descends. It has to be waiting for them, already built, already tested, before they commit to going down. Phase 3 follows. Habitat modules, almost certainly a mix of rigid metal shells and expandable inflatables, are landed near the pit, driven to the rim, and lowered through the shaft to the cave floor. Rigid modules give known volumes and predictable structural performance. Inflatables, of the kind Bigelow Aerospace and now Sierra Space, developed for use in orbit, give far more habitable volume per kilogram of launch mass. And on a mission where every kilogram costs a fortune, that difference matters enormously. The baseline most academic studies converge on is a hybrid design, a spine of rigid modules containing life support systems, power management, and airlocks, connected by inflatable soft-shell sections for living quarters, laboratories, and agricultural bays. Inside a cave, that baseline makes particular sense. With more than 100 meters of basalt overhead, the module skin does not have to stop radiation. It only has to hold air. The rock handles everything else, and an inflatable is well suited to a job that reduced to a single requirement. Then comes Phase 4. And this is where the gap between concept and hardware becomes most visible. The debris field on the cave floor has to be cleared before any module can sit on it. The field is not gravel. It is a chaotic pile of basalt boulders ranging from cobblestones up to blocks the size of shipping containers, tumbled together over billions of years, some of them stable, some precariously balanced, some likely to roll from a single nearby vibration. Robotic machines will have to sort the field, move the largest blocks to the chamber walls, break medium ones with rock hammers or chemical cutters, and grade the remaining rubble into a surface flat enough for structures to rest on. On Earth, this kind of work uses equipment weighing tens of tons, drawing hundreds of kilowatts of power. On the Moon, the machines will be smaller, lighter, and cable-powered from the surface. The 1/6 gravity changes both what they can lift and how released debris behaves. A boulder tipped on the Moon drifts slowly downward, keeping its rotational momentum, landing with less crushing force than it would on Earth. That is helpful in the sense that the machines do not need to be as strong. It is dangerous in the sense that a slowly tipping block gives a nearby robot plenty of time to be knocked off balance before it settles. None of these machines exists yet in flight-ready, lunar-tested form. Several prototypes have been demonstrated in Earth laboratories, from JPL, from teams at the Colorado School of Mines, from commercial partners. Each solves part of the problem: excavation, grading, autonomous navigation, manipulation of large, irregular objects. But none combines all of those capabilities, and none has been tested in real lunar gravity, real lunar dust, and real vacuum simultaneously. The first pit floor construction operation, whenever it happens, will be the largest single robotics test ever attempted beyond Earth orbit. That is not a boast. It is a description of the gap. Phase 4 has one more requirement after the floor is cleared. The cavity walls need inspection for loose material that might eventually fall onto the habitat below. Rock that has been stable for 1 billion years may have fractured sections near the ceiling collapse zone, and the overhead material closest to the pit opening has been subjected to thermal cycling that deeper sections have not. Some engineering concepts address this by placing modules inside a protective outer shell, a semi-rigid enclosure providing a second pressure barrier and a smoother interior surface. Others place modules directly on the cave floor, connected by flexible tunnels, and accept the ceiling risk as manageable. Either approach requires the same underlying judgment, a detailed survey of which ceiling sections are stable and which are not, carried out by robots before any crew enters. And here is where the most quietly counterintuitive consequence of cave construction becomes clear. Every pit is a different shape. The Tranquillitatis conduit has a specific width, a specific ceiling height, a specific floor extent, a specific orientation relative to the shaft. Another pit at another location will have different dimensions entirely. There is no generic lunar pit to design for, which means every settlement has to be built around the unique geometry of its particular chamber. Nothing is standardized. Each pit demands its own architecture. The modular, mass-producible moon base of popular imagination does not survive contact with the actual shape of the moon's interior. 4 phases in, and the settlement still has no power running to it, no air circulating through it, no water moving inside it, no communications link connecting it to the surface above. Those connections make up the 5th and most complicated phase. That is where the real engineering difficulty lives. Power comes first, because nothing else works without it. The assumption most people carry about a moon base involves solar panels. Clean, proven, scalable. You unfurl them on the surface, they capture sunlight, they charge batteries, the base runs. It seems obvious. It seems solved. But here's where it gets strange. At the low latitudes where most of the lunar pits sit, including the Tranquillitatis conduit, the moon does not offer a reliable solar resource. It offers 2 weeks of sunlight, followed by 2 weeks of complete darkness. Not a brief shadow, not a cloudy afternoon. 14 days with no sun at all. 14 days during which every solar panel on the surface produces nothing. Not a manageable inconvenience, a fundamental disqualification. A handful of ridges near the lunar poles receive near-continuous sunlight because of the moon's slight axial tilt, catching the sun the way a sundial catches it at shallow angles for most of the year. But those ridges are rare, location-specific, and far from the Mare where the known pits are concentrated. For a settlement at Tranquillitatis, 2-week solar blackouts are not an edge case to plan around. They are the baseline condition. So almost every serious engineering concept for a lava tube settlement arrives at the same answer: nuclear. In 2022, NASA awarded contracts to 3 industrial teams to develop preliminary reactor designs under the Fission Surface Power Project, developed with the US Department of Energy. One team was led by Lockheed Martin. One was led by Westinghouse. A third, smaller company formed the third team. The target was a reactor delivering roughly 40 kilowatts of electrical power, continuously, for at least a decade. 40 kilowatts is modest. It is approximately the power draw of a small hotel. For a settlement stripped to its minimum viable configuration, keeping lights on, life support running, and heating systems working, it is a lifeline. The reactor itself is small enough to fit on a single lander. In most designs, the core sits in a shielded housing on the surface, connected to a heat rejection system that radiates waste heat into the vacuum through large flat panels, and to a power conditioning unit that manages the electrical output. Cables run from there down the shaft, across the debris field, and into the modules below. The reactor does not care about the 2-week night. It does not care about temperature extremes. It delivers steady power around the clock from enriched uranium fuel that arrived in a single shipment, and will not need replenishment for years. That sounds like an elegant solution, but the problems begin the moment you try to plan beyond that first decade. Nobody has yet worked out a practical procedure for refueling a nuclear reactor on another world. The concepts currently on paper do not attempt it. They assume the reactor runs until its fuel is spent, then gets shut down and replaced. A new reactor arriving on a fresh lander. That means every long-term settlement plan implicitly commits to a slow, continuous stream of nuclear payload launches from Earth, stretching across decades. Each launch carries nuclear hardware. Each launch needs to be licensed, insured, and eventually disposed of on a body that belongs, in some sense, to no nation and every nation. The regulatory framework for that does not yet exist. And the reactor still sits on the surface. The cave protects the people inside it. The reactor, by necessity, is outside, sandblasted by micrometeorites, thermally cycled through the lunar day and night, coated in electrostatically charged dust. Its independence from sunlight does not exempt it from the environment overhead. It needs robotic servicing. Robotic servicing needs spare parts. Spare parts need to be launched. Every layer rests on the one beneath it. Then there is the cable running down the shaft. 100 meters of cable in a lunar environment is not a trivial object. It can be cut by falling debris. It can degrade under radiation and thermal stress over years. It can develop a fault at a point that robots cannot easily reach. So redundancy is required. 2 independent feeds from 2 separate reactors. Backup batteries inside the cave sized to carry the settlement through hours or days of total power loss. Emergency systems triggerable from anywhere in the habitat, not just from a single control room. Every redundancy costs mass. Every kilogram of mass must be launched from Earth. Every launch is a new opportunity for something to fail before it arrives. The settlement is only as good as its worst single link. Power is the first utility. Air is the second, and it is harder. A closed-loop life support system inside a cave must do everything a spacecraft does. Scrub carbon dioxide from the atmosphere. Generate oxygen to replace what the crew breathes. Control humidity. Filter particulates. Manage trace chemical contaminants that build up in any enclosed space over time. But it must do all of this at a scale far larger than any crewed spacecraft has attempted. And it must do it continuously for years, not months, with resupply arriving at best every few months, and possibly only once a year. The International Space Station is the current state of the art. It recycles roughly 90% of its water and about half of its oxygen. It is a remarkable engineering achievement, and it still requires constant resupply from Earth. That is not an option for a cave settlement, not at the same dependency level. The target for a cave settlement is not 90% water recycling and 50% oxygen recovery. It is 95%, 98%, ideally beyond, and no such system has been demonstrated at habitat scale for the duration required. Every test of closed-loop life support to date has revealed some new failure mode, a subtle contaminant accumulating in the water supply that the filters did not anticipate, a bacterial bloom in a moisture-rich section of the recycling equipment, an unexpected consumption rate of a filter medium that ran out 3 weeks ahead of schedule. In a test facility on Earth, each of those failures is a research finding. In a lava tube, with the nearest resupply 3 days away on a functioning rocket, if the launch window is open, each of those failures is a survival threat. Think about what that means for the people inside. The atmosphere is not a place, it is a machine. Every molecule of air the crew breathes passes through hardware before it comes back. Every sip of water is the output of a recycling process that must not fail. The cave provides the walls and the ceiling, but it does not provide any of this. The atmosphere must be built, maintained, and continuously repaired by people who cannot simply go outside and breathe if something goes wrong. There is no outside, not in any meaningful sense. Water adds its own dimension to the problem. At low latitude near the Maria, there is no accessible water ice. The polar deposits are real. Measurements from the L-Cross mission and subsequent surveys suggest more than 600 billion kilograms of ice may exist in permanently shadowed craters at the lunar poles. That is an enormous resource, but those deposits are thousands of kilometers from Tranquillitatis. They might as well be on a different world. So a settlement near Tranquillitatis must import its water from Earth, or extract it from separately imported oxygen and hydrogen, or in the longer-term ship it from the poles using surface transport that itself does not yet exist, and would have to be built and operated across hundreds of kilometers of challenging terrain. Every option is expensive. Every option requires things to work in perfect coordination with other things that must also work perfectly. A wall that is not finished is a delay. An air recycling loop that fails is something else entirely. And with the list of dependencies growing longer every time you look at one more system, the fifth phase of construction is where the margin disappears. The biggest challenge of the settlement is not the shaft, not the debris field, not the ceiling. It is keeping the whole chain intact every day for years. And the systems that define that chain have not all been built yet. And the systems that define that chain have not all been built yet. It would be comforting to think that moving underground leaves the surface's problems on the surface. It does not. Most of them come down with you. Start with dust. The regolith problem does not vanish when you descend the shaft. It moves. Every rover that rolls down into the cave carries dust on its wheels, on its chassis, on every surface that touched the ground above. Every construction operation on the debris field kicks up new material. Every airlock cycle transports some from the exterior into the pressurized volume. And once dust is inside, the moon's gravity makes it worse, not better. In 1/6 gravity, fine particles do not settle quickly. They hang. They drift. They cling to surfaces by electrostatic attraction, the same charge the surface dust has always carried. They coat filters. They work into bearings. They grind down every mating surface they contact. NASA's Dust Mitigation Working Group has studied this problem for more than 10 years. Their conclusion is not a solution. It is a set of strategies: magnetic filters, electrostatic curtains, multi-stage airlocks with progressively cleaner chambers, each stage reducing the contamination load before anything passes into the main volume. Dedicated changing rooms outside the pressurized area where suits are cleaned and stored before anyone crosses the threshold. Each strategy adds cost, each adds mass, each adds complexity, and none of them eliminates the problem. They manage it. But here's where it gets strange. The cave does not start clean. The Tranquillitatis conduit has been sealed from above for billions of years, but its interior is not a sterile room. The ceiling collapse that opened the pit scattered debris across the floor. Billions of years of thermal cycling and micrometeorite impacts have shed fine material from the walls and ceiling ever since. That resident dust is chemically identical to surface regolith. Same jagged shards, same silica, same reactive dangling bonds. Any construction inside, any rover driving across the floor, any drilling of anchor bolts, any module being moved into position, kicks that material into the vacuum of the cave interior. In 1/6 gravity, it hangs in a slow drifting cloud for hours, settling on every surface, and gets tracked into the habitat when the airlocks first cycle. Some of it will still be there years later. Radio cannot help you call for help through the rock. On the near side of the Moon, direct radio contact with Earth is possible from the surface almost any time Earth is above the horizon. Inside a cave, that contact is gone. Radio waves do not pass through 100 meters of solid basalt any more than sunlight does. Every message between the settlement and Earth must route through a surface relay. That relay must be powered, protected, robotically maintained, and duplicate for redundancy. Because if the single relay fails, the settlement is cut off, not slowed down, not inconvenienced, cut off entirely. Any surface exploration, once crew members have suited up, requires either direct line of sight to a relay at the rim, or a chain of smaller relays across the terrain beyond. There is no cell network. Every square kilometer of coverage has to be built, antenna by antenna. Navigation is no better. GPS does not exist at the Moon. No satellite constellation provides precise position fixes to anyone on the surface. NASA has proposed a system called LunarNet, and ESA a similar initiative called Moonlight, that would eventually provide lunar navigation and communication services. But neither is fully operational as of 2026. Both are in early implementation. Until they exist, every rover, every suited worker, every drone, every machine must navigate by dead reckoning, by visual landmarks, or by short-range radio triangulation from local beacons. And inside a cave, even those beacons must be installed and maintained by hand. There are no natural landmarks in a chamber no one has ever entered. There is no view of the sky to reset a position by. If your inertial navigation drifts, you are lost inside a completely dark room the size of a large warehouse, wearing a suit that will run out of air in a few hours. Then comes the single, most frightening word in the vocabulary of underground habitation: evacuation. Every terrestrial building code, every mining safety regulation, every submarine design standard is built around one principle. People trapped in a hostile environment need multiple independent ways out. Not one, multiple. The baseline lava tube settlement has one shaft, one elevator or ramp, one route to the surface. If the elevator jams, the ramp is blocked by rockfall, a subsidence event makes the debris field impassable, or a surface event disables the machinery at the top. The people below are sealed in. They wait until it is fixed. Rescue from Earth is 3 days away at the fastest, and that rescue cannot descend into the pit if the access infrastructure is already broken. The engineering response is straightforward to name and nearly impossible to execute. Build multiple access points. That requires either drilling additional shafts through the ceiling from above, a construction project of extraordinary complexity, or discovering a second natural pit that connects to the same tube. No confirmed pit has yet been found with a second connected skylight. Some concepts imagine future settlements along tubes with multiple openings, but whether such tubes exist and whether their skylights open into the same continuous volume will not be known until missions map an interior in detail. Until then, every proposed cave settlement is a facility with a single door, and everyone inside has to trust that the door will keep working. Wait, this is not a minor deviation from normal engineering practice. Mining regulations, building codes, submarine standards, they all prohibit single access point facilities precisely because one failure can trap everyone with no alternative. The lava tube baseline design, as currently conceived, violates every safety norm human civilization has developed from centuries of working in hostile environments. The Moon itself adds one more complication. The Tranquillitatis conduit has sat under its ceiling for roughly 3 billion years, and there is no reason to expect sudden catastrophic collapse. But there is also no reason to assume uniform stability along the entire length of the passage. Apollo-era seismometers placed on the surface recorded moonquakes, driven partly by tidal stress from Earth's gravity and partly by thermal expansion and contraction across the fortnightly cycle. Most of those quakes were gentle, but some shallow moonquakes, originating in the upper crust, reached magnitude 5 or higher, capable of structural damage to a surface building near the epicenter. Inside a cave, a moderate quake could dislodge loose ceiling material, shift the debris field, or tear anchor points away from the walls where cables and utilities are attached. Periodic rockfall from the ceiling is not a hypothetical worry. It is a design constraint. Any settlement must be built assuming the interior will occasionally rearrange itself. Not simpler than a surface habitat. More complicated. The cave is still a shelter. That is the honest accounting. It solves problems that would otherwise be nearly unsolvable. The rock overhead handles radiation, thermal cycling, and micrometeorite bombardment in a single geological feature that costs nothing to maintain. That advantage is real and it is enormous. But turning the conduit into a functioning settlement demands engineering of extraordinary depth. The access shaft, the vertical transport, the modules, the power system, the closed-loop air supply, the water supply, the thermal control, the communications relay, the navigation beacons, the dust mitigation systems, the seismic monitoring, and the emergency escape infrastructure, all designed, delivered, and installed before a single crew member moves in permanently. And every piece of that infrastructure is a piece that can fail. In an environment where failure has consequences, no terrestrial construction project has ever had to contemplate. That is the ledger so far. The debit column is long. The question now is what life inside that ledger would actually look like. Engineers have a name for all of that, not a vague name, a precise one, with a long history behind it. The phrase is defense in depth. It comes from the safety analysis of nuclear reactors, where the governing principle is that no single barrier between a hazard and a human being should ever be assumed reliable. Every critical function must be protected by multiple independent layers. If one layer fails, the system remains safe. If two fail simultaneously, a third is still holding. The assumption built into the philosophy is not that failures are unlikely. The assumption is that failures are inevitable, and that the only honest response to that fact is to plan for them in sequence, not in isolation. On the lunar surface, defense in depth means multiple pressure barriers, multiple oxygen systems, multiple power sources, multiple communication paths, and multiple escape routes, all working in parallel, none of them the single thing that everything else depends on. Inside a lava tube, it means all of that plus additional layers to cover what the tube introduces. The single access point, the potential for rockfall, and the impossibility of a quick rescue if something goes wrong in the wrong order. But here's where it gets strange. Nobody has ever actually built a facility that had to meet this standard. Not for years. Not with no external support. Not anywhere on Earth. The closest analogies are the ones engineers reach for first. Nuclear submarines, deep-sea research stations, Antarctic winter bases. All three operate in hostile environments, cut off from easy help, dependent on their own systems for the duration of their stay. All three are real, proven, and understood. And all three fall short in exactly the same kind of way. A nuclear submarine can surface. If something goes catastrophically wrong below, the first option is to bring the boat up and open the hatch. That option exists. It is always there. A deep-sea research station can be evacuated to a support ship sitting directly overhead, with a dive team on standby and a decompression chamber waiting. The infrastructure of rescue is part of the mission before the mission starts. An Antarctic winter base can be resupplied by aircraft when conditions allow. Not easily, not cheaply, and not always quickly. But the sky is a viable pathway if the situation demands it. A lunar cave settlement has none of these fallbacks. Not one. If something goes wrong inside the conduit, the people inside are alone with the problem for as long as it takes to fix it, or to survive it. There is no surfacing, there is no support ship overhead, there is no flight path that opens when conditions improve. The nearest source of help is a 3-day minimum transit away, and that help cannot descend if the access infrastructure is what failed in the first place. The submarine analogy, the Antarctic analogy, the deep sea analogy, each of them carries an escape clause the moon settlement does not have. Meeting defense in depth under those conditions, for years, with no external support, is a standard no Earth facility has ever been held to. Not a harder version of a familiar standard. A different standard entirely. None of which is a reason not to try. It is a reason to be honest about what trying means. A permanent settlement inside a lava tube is not a village in a picturesque cavern. That image is wrong in almost every detail. What it actually is a small industrial facility packed with machinery, connected to the surface by a single lifeline, protected from a hostile universe by a thin metal skin and a ceiling of ancient rock. Its survival depends on every one of its systems working every day. In an environment where the only backup for a broken system is another system designed at the same time by the same people, shipped on the same rockets. The redundancy is real. The margins are not generous. And the fallback for the fallback is a shorter list than anyone would like. That is the honest picture. Not a moon base in the popular sense of the word. An engineered lifeboat held together by the same philosophy that keeps nuclear reactors from melting down, applied to a place where the reactor can never be shut down and the operators can never leave. And this is the settlement people will have to live inside. Not for a mission, not for a rotation with a clear end date on the calendar. For years. For careers. Perhaps if the settlement holds, and the generations follow, for the rest of their lives. What that actually feels like is where the story becomes something other than an engineering problem. Waking under artificial light every morning, the same spectrum, the same angle, calibrated by a timer rather than a sun. Exercising against a gravity that quietly weakens bone and muscle with no particular urgency. Just a slow, patient arithmetic of loss. Breathing recycled air that has been through the same lungs for months. Scrubbed and recirculated and scrubbed again by the same machines running the same chemistry in the same cave. Working shifts in a dust-choked airlock. Suiting up and unsuiting in a room designed to keep two worlds from contaminating each other. Going months without seeing an unfiltered horizon. Going years without rain. It becomes a question of what it means to be human, inside a place that was never built for people. The engineering gets you to the cave. What happens inside the cave? What people carry with them? What they lose, what they find, what they build out of the hours between the maintenance shifts. That is a different kind of question. And it is the question the next part of this story is about. So picture it from the inside. The day begins not with a sound, but with a light. A soft, warm band of LEDs in the ceiling of the sleeping cubicle, brightening slowly across half an hour, imitating a terrestrial sunrise no one here can see. The resident wakes the way people have always woken to morning light, because the human body still requires that signal, still runs on a clock tuned to a roughly 24-hour cycle, still falls apart when that rhythm is violated. The clock doesn't know it's on the moon. It doesn't know the actual sun outside, right now, in the middle of a 14-day lunar night, is nowhere near the horizon. It knows the light, and the light says morning. So morning it is. The resident sits up in 1/6 gravity. And here, immediately, is the first strangeness of the day. Not a dramatic strangeness. A quiet one. The body drifts a little farther than it intended on every motion. The pillow doesn't stay where it was put. A hand reaching for the wall finds it half a beat late. It's not painful, and it's not disorienting in the way a carnival ride is disorienting. It is simply wrong in a small, permanent way. The constant low-level reminder that the body evolved for a planet with 6 times as much pull, and this is not that planet, and it never will be. Then, the resident ignores it and gets on with the day. But here's where it gets strange, if you've been picturing this the way most people picture it. Because the imagination, given half a chance, makes this beautiful. It makes it a vast, softly lit cavern with ferns along the walls, and families crossing a wide plaza, a skylight glowing overhead. Something between a greenhouse and a cathedral. That image is wrong. Not slightly wrong. Completely wrong. The cavern, if there is one, will be mostly dark, most of its volume cold and unused, the modules occupying a small fraction of the available floor. The interior of an underground lunar settlement will look and smell and feel something like a cross between a submarine, a laboratory, and a very small greenhouse. It will bear no resemblance to any environment humans evolved to occupy. No window opens onto anything worth seeing. Beyond the fabric wall of the sleeping cubicle is an inflatable module. Beyond that, the floor of a lava tube. Beyond the tube ceiling, 100 meters of ancient basalt. Beyond that, the lunar surface in the middle of its long night, at near negative 70 degrees Celsius, where nobody has been outside for a week. There is nothing to look at. There is no window. The light is all there is, and the light is engineered. It runs warm in the morning, blue-white by midday, amber by evening, dim red in sleeping areas at night, cycling through a 24-hour Earth day that has no connection to the actual sun. Most serious concept studies assume residents will keep this cycle, because the alternative is worse. The lunar day is 29.5 Earth days long. Living on it would mean staying awake for 2 Earth weeks, sleeping for 2 more. No one has tried that. The research on what mismatched circadian timing does to cognition and mood and immune function is unambiguous, and it is not encouraging. So the settlement runs on Earth time, the clocks count Earth hours, and the only sunlight any resident will feel on their skin is the kind that comes out of a calibrated LED array. That has consequences. Sunlight on skin produces vitamin D using ultraviolet wavelengths that LEDs can approximate but must be deliberately included and medically monitored. ISS crews already manage this, since even the station's windows filter out the UV the skin actually needs. Underground, the problem is the same but more complete. Every supplement, every controlled UV lamp session, every blood test to verify the levels are holding becomes part of the routine. The body is not broken. It's just operating in a place it was never designed for, and staying healthy inside that place requires work. The same logic governs the first 2 hours of every morning. Not 2 hours of personal choice, 2 hours of medical prescription, exercise on resistive machines that force the muscles and skeleton to work against loads they would otherwise never encounter, because 1/6 gravity does not provide them. The popular image of low gravity is the Apollo bounding walk, easy and almost playful, a person barely touching the ground. But those astronauts spent a few days on the surface. Nobody knows what happens to a body that lives in 1/6 gravity for years, because nobody has ever done it. Every number comes from extrapolation, from zero gravity studies, from bed rest experiments, from short animal tests. What the extrapolations broadly agree on is this: 1/6 gravity is not enough. Not enough to preserve bone density, not enough to maintain muscle mass, not enough to keep the cardiovascular system working the way it was built to work. At zero gravity, astronauts on the ISS lose roughly 1% of weight-bearing bone density per month, despite spending 2 hours every day on resistive machines. At 1/6 gravity, the loss should be slower. But slower is not zero, and a career in that environment, across years, may leave changes that don't reverse. Vision alterations, cardiovascular deconditioning, shifts in immune function, a slow and patient arithmetic of loss that the body doesn't announce and the environment doesn't apologize for. So the 2 hours are not optional. Missing them produces measurable declines within weeks. The settlement's medical officer will spend a large portion of their working day managing the consequences of an environment the body was never designed to occupy, which means the medical officer will be busy. After exercise, after the shared meal in the common area, the day divides into work shifts. And here the settlement reveals what it actually is. The air circulating through the modules has been through those same lungs before. CO2 stripped by scrubbers, oxygen regenerated by electrolysis, broken out of water molecules by electrical current, humidity managed, trace contaminants filtered, all of it running continuously, all day, all night, every day the settlement exists. When the systems work, nobody notices. When they fail, everybody does. A CO2 scrubber that stops produces symptoms within hours. Headache, drowsiness, judgment beginning to slip, long before anyone realizes the cause. The atmosphere inside the settlement is a machine, not a place. It exists only because a set of pumps and filters and reactors are running continuously. And if they stop, so does everything else. The water follows the same logic. Every liter has been through someone before. Urine into a distillation system recovering about 90% of its water. Humidity from the cabin air collected and filtered. Hygiene wastewater treated and returned to the loop. A resident who has been there a year has drunk their own purified water, filtered from urine, hundreds of times. This sounds stranger than it is. The water in a glass on Earth has passed through the bodies of countless animals across billions of years of geological history. The difference is that Earth has an entire hydrosphere and biosphere doing the recycling across an ocean-sized system with an enormous margin for error. In the settlement, a set of stainless steel canisters does it, and the canisters have to work. Food arrives freeze-dried from Earth and grows imperfectly under LED arrays in the agricultural bays. Lettuce, kale, spinach, herbs, tomatoes, peppers, strawberries, all grown in soilless hydroponic systems in compartments that smell faintly of wet roots and warm plastic. The calorie math for growing staple crops in a space this small rarely works out in their favor. Wheat and rice need more area, more energy, more processing than the bays can support. But the agricultural sections survive in concept study after concept study, not purely for the calories. Antarctic winter cruise and the sealed habitat experiments of the 1990s produced a consistent result. People in artificial environments derive something disproportionate from living plants, not just nutrition, something harder to measure. The visible evidence that something other than a pump or a fan is participating in the life of the place. Everything else in the settlement is machinery. The plants are alive. The living space around them is not generous. A crew of 8 to 12, perhaps 4 or 5 modules each the size of a shipping container, sharing a total pressurized volume roughly comparable to a modest single-family house, except that the house also contains the laboratories, the workshops, the agricultural bays, the medical facility, the storage, and the life support equipment. Each resident has a sleeping cubicle roughly the interior volume of a compact car, a bed, a small workstation, a locker, a screen. Everything else is common space, shared and timed and rotated. Meals together, exercise in a shared bay, hygiene facilities scheduled, communications with Earth private in content, but bandwidth limited and archived for engineering review. The literature on what this does to people is large and consistent. Antarctic stations, submarines, offshore oil platforms, orbital stations, every environment where trained and carefully selected professionals have been confined for long stretches has produced the same pattern. The first weeks run on novelty. The first months settle into productivity and routine. Then, somewhere around the 3 to 6 month mark, something shifts. Small conflicts that seem manageable become chronic. Minor irritations compound. Cognitive performance edges down. Motivation flags. Researchers call it the third quarter effect, and it does not discriminate. It arrives in screened, trained, motivated professionals who chose to be there and knew the conditions before they arrived. It is not a failure of character, it is a predictable feature of the environment. Well-designed missions manage it, through crew selection and scheduled family contact and rotating leadership and whatever variety and privacy the space allows. But in an underground lunar settlement, the environment allows very little, because the sky is not there. There is no walk outside to clear the head, no change in weather to break the sameness of the days, no view that extends more than the length of a module. The ceiling is rock, the walls are fabric and metal, the light is the same light it was yesterday, and tomorrow, the light will be the same again. What people build inside that constancy, what they carry through it and what they put down, matters more than any engineering diagram has yet tried to measure. Most days, the sky is just not there, but sometimes when it is your turn, you go up to meet it. Getting to the surface requires suiting up, cycling an airlock, boarding a cage elevator, and riding a cable through 100 meters of shaft. And even then, what waits at the top is not the sky of childhood imagination. It is a grey plane under a black void. The sun, a white disk so bright, the visor darkens the moment it appears. And the Earth, if the settlement sits on the near side, hanging fixed above the horizon, blue and white and cloud marbled, unchanging. It does not rise. It does not set. It sits in the same position, day and night, week after week, month after month. Beautiful, yes. And also, in a way that is difficult to convey until you have thought about it for a while. Unnerving. Every image of home is fixed in one place. Unavoidable, unapproachable, simply there, forever. And the trips are rare. Every excursion is a radiation dose, a suit-up checklist, a buddy verification, an airlock cycle, a careful log entry. The medical officer tracks each resident's cumulative surface time against a strict annual limit. When that limit is close, the excursion is cancelled. Nobody receives extra hours. Nobody is exempt. Most residents, most of the time, are not outside. They are under the rock, in the same rooms as yesterday, in the same rooms as tomorrow. The shape of that life is worth naming plainly, waking under artificial light, exercising against a gravity that is quietly reshaping the body, breathing air that has been through everyone's lungs, drinking water that has been through everyone's kidneys, eating food grown in racks under lamps, working in a small volume with the same small group, speaking to Earth across a signal delay of just over 1 second, short enough for conversation, long enough to feel it every time, waiting for the resupply that arrives every few months, carrying letters, small gifts, replacement parts, and occasionally a new crew member or a departing one, never feeling wind, never feeling rain, never smelling anything that was not carried up from Earth or grown in the agricultural bay, never standing outside without a full personal life support system, never, in the ordinary sense of the word, going anywhere, except on excursion days. Follow one resident through it. The morning begins like any other. Artificial sunrise, breakfast in the shared galley, a schedule check on a handheld, But today is a surface day, and from the moment breakfast ends, the pace changes. Every step is proceduralized. Every step is verified by another human before proceeding. The clearance is not a formality. First stop is medical. The medical officer takes baseline measurements: blood pressure, heart rate, blood oxygenation, hydration. Then a review of the cumulative radiation exposure log. Every additional hour on the surface is measured against a career total that determines how long this resident can remain part of the settlement at all. If the numbers are close to the limit, the excursion is cancelled. Within allowance, cleared. Next is the pre-breathe. If the habitat runs at reduced pressure with elevated oxygen, as many designs assume because lower pressure means thinner walls and less launch mass, the resident is already partly acclimated. If the habitat runs at full earth pressure, the resident spends an hour or more breathing pure oxygen through a mask, purging dissolved nitrogen from the blood. Without that process, stepping into the suit's lower pressure environment would be like a diver ascending too fast. The bubbles that form in the bloodstream can be fatal. The pre-breathe is boring. It is also non-negotiable. Then, suit up. The personal suit is docked to a port on the outer airlock wall. The resident climbs in through the back hatch, one leg at a time, seals it, and begins pressurization. The checklist runs as the suit inflates. Helmet seal, comms, biometric telemetry, water supply, oxygen supply, CO2 scrubber, cooling loop, radiation dosimeter, emergency beacon. Each item confirmed by another resident watching from inside. Only when every item is green does the suit undock and the resident step away from the wall. Then the walk to the shaft. Several hundred meters across the cave floor, past storage yards and equipment bays. Then the elevator, an industrial cage for cargo and personnel, cable-powered from the surface. The ascent takes several minutes. Through the mesh sides, the cave walls fall away. The circular patch of black sky at the top grows larger. The surface arrives without ceremony. The lift stops at a rim platform. The resident steps out into unfiltered lunar daytime. For a moment the sun is a blindingly bright disk against a completely black sky. The visor darkens. The horizon reveals a grey plain of undulating regolith, dotted with craters, curving away shockingly close. The moon is small. The horizon feels almost walkable. The earth hangs above it, fixed and enormous and impossibly far. Then the work begins. Inspecting a solar array, servicing a communications relay, checking a scientific instrument in person. Done quickly, done methodically, with constant attention to suit telemetry. Radiation is monitored continuously. Any solar particle warning, any suit anomaly, a slow pressure leak, a cooling loop irregularity, a suspicious biometric reading, triggers an immediate abort. The resident works with the awareness that they are protected from a hostile vacuum by a machine, and that every minute the machine keeps working is a minute they get to keep breathing. Then the return. Platform, lift, shaft, cave floor. Dock to the suit port, climb out, post-excursion medical check, radiation dose logged, suit maintenance requested for any anomalies, and then, in the ordinary way, back to the day's other work. By evening, the resident is in the galley comparing notes with someone who spent the day in the agricultural bay. The excursion, which felt enormous while it was happening, has been reduced to a line entry in the settlement's log. 6 hours on the surface, 1.5 millisieverts accumulated, no anomalies, return to routine. This is what makes the life so quietly strange. The extraordinary, a trip to the surface of another world, becomes ordinary because it has to. If it stayed extraordinary, the psychological load would be unmanageable. So the culture absorbs it. Every resident goes when scheduled, does the work, comes back, treats it as a workday, because on some level, that is what it is. The frontier is not adventure. The frontier is a workplace with unusual hazards, unusual procedures, and unusual paperwork. And underneath all of it, every resident carries a fact that never goes away. The settlement is not a place, it is a machine. The cave provides radiation shielding, but everything else, pressure, air, water, food, temperature, light, the signal home, depends on hardware that has to keep working every second. There is no ecosystem outside the door, no local biology to help. If the systems fail catastrophically, and the access shaft is blocked, and the rescue mission cannot arrive in time, everyone inside dies. This is not a hypothetical to be minimized, it is the fundamental condition of the environment. lived with the way a submariner lives with the sea overhead, the way an Antarctic winter overcrew lives with the storm outside, the way an astronaut lives with the vacuum on the other side of the hatch. They live with it because they have to. After a while, they stop thinking about it consciously. But it is always there. Zoom out now. The moon was supposed to be the easy one. The near neighbor, the 3-day journey, the stepping stone where humanity practiced for the harder destinations beyond. It may still be all of those things, but if the safest way to live there requires moving underground into ancient volcanic tunnels whose walls are unmapped and whose ceilings could shed basalt onto whatever we build, then the frontier is not a shining city. The frontier is a hole. More precisely, it is what humans can build inside a hole the moon carved for them 1 billion years before the first cells appeared in Earth's oceans. This is not defeat. In some ways, it is the opposite. What an underground settlement demonstrates, if it succeeds, is not that the moon has become casually livable. It demonstrates that humans can build a piece of Earth, a small, carefully engineered, closed-loop, radiation-shielded piece of Earth, and place it on another world, and it will keep working. Not because the world outside is friendly, because every system was designed, tested, delivered, and installed on the assumption that the world outside will never help. The moon does not become habitable, a fragment of Earth is smuggled inside it. The residents are not lunar people, they are terrestrials in exile, keeping their own biosphere alive through machinery brought from a planet 250,000 miles away. For a long time, the popular framing has drifted towards something grander, humans becoming multiplanetary, spreading across the solar system and adapting to new worlds the way ancestors adapted to Earth's deserts and tundras and coastlines. The cave settlement suggests this framing is wrong, not slightly wrong, dramatically wrong. No biological adaptation is happening. What is happening is that humans transport the specific narrow envelope of conditions in which their biology functions, the pressure, the temperature, the atmosphere, the radiation environment, the gravity as best it can be compensated, and reproduce that envelope at enormous cost inside a foreign environment that would kill them in minutes if it ever touched them directly. The envelope is what expands. The people inside remain physiologically exactly what they were on the day they left Earth. Even in the most successful version of this settlement, the connection to Earth is total. Every kilogram, every message, every replacement filter, every crew member arrives from a planet that is still, and probably always will be, the only place where these residents can walk outside without protection and simply breathe. There may one day be children raised inside that rock. The medical questions are enormous. The effects of 1/6 gravity on prenatal development and early childhood are completely unknown. The ethical questions are larger still, and whatever answers those children's parents arrive at, they will arrive at them underground, under artificial light, in recycled air, with the Earth fixed in a black sky they will rarely see. Humanity's first realistic path to a lasting presence on the moon may run not across the plains where Armstrong and Aldrin walked nearly 60 years ago, but beneath them, down through skylights, across debris fields, into conduits sealed since the last eruptions cooled, inside modules holding air against vacuum on one side and stable ancient rock on the other, under a ceiling of volcanic basalt providing, for free, the shielding that would otherwise require moving a small mountain. And inside that shelter, a small community doing every ordinary act of human life. Sleeping, eating, arguing, laughing, calling home, under artificial light, in recycled air, in 1/6 gravity, with the moon's surface overhead and the Earth 250,000 miles away. It may in time become a place, the first lasting human community on another world, but not a city on the moon, a sealed transplant of Earth's own biosphere, buried inside the moon and protected by the moon from the very environment that the moon itself provides. Not a shining base on a bright plain, a sealed shelter beneath one. Not a second Earth, a fragment of Earth, smuggled into the rock of another world, kept alive by the constant, careful attention of the people who chose to live inside it. The safest way to live on the moon may indeed be to retreat beneath its surface, and that retreat may become, in the coming century, the beginning of humanity's first lasting home beyond Earth. But it will not make the moon habitable. It will only make it possible to survive there. And the difference between those two words, habitable and survivable, is the difference between a place where you belong and a place where you have brought your belonging with you. The moon is not our second home. It may one day soon be the first world we successfully hide inside,